Okay, everybody, I'm going to walk you through this set of problems here. Once again, this is unedited. Hopefully it goes smoothly. Doubt if it does. Hopefully I catch my mistakes. If I make any, correct myself, etc. Anyway, let's get started. For each of the following, determine if it is a probability distribution, and if not, explain why. Okay, some of the things you have to recall regarding a probability distribution is the probability of any particular event is always greater than or equal to 0 and less than or equal to 1. In other words, probabilities cannot be negative or larger than 1. Second, the total probability has to add up to 1. So looking at our first set, our outcomes are represented here by 1, 2, 3, and 10. Here are the associated probabilities. The probability of getting a 2 is a negative 0.5. That can't happen, so this is not a probability distribution. So the answer to this is no. For our second one, here are the possible outcomes. We don't really care about the outcomes. Outcomes are just what could happen, right? So we're concerned about the probabilities. All the probabilities are somewhere between 0 and 1, so that works out. But if you add up these probabilities, if you add them up, you get 0.99, which is less than 1. The total probability, that is the probability of anything happening, is equal to 1. So that's not the case, so the answer to this one is no. For number 2, you're being asked to determine the mean and the standard deviation for a given population. Here, the possible outcomes are 1, minus 1, and 2, and here are the associated probabilities. When you're giving the outcomes and the associated probabilities, the mean is actually what we call the expected value. So what we need to do is multiply each outcome to the associated probability. All right? So in other words, the expected value of a random variable is the sum of each data value multiplied to the probability of that data value. So working this problem here, 1 times 0.25 is 0.25. A negative 1 times 2.25 is minus 0.25. And then 2 times 0.5 is 1. When we add this all up, we get 1. So the mean is equal to 1. The standard deviation associated with a population is given by the following formula. Sigma is equal to the square root of the sum of you multiply the difference between each data value and the mean, okay, squared, times the probability of that data value. So this is the formula for the population standard deviation. I need to calculate the difference between the data value and the mean, squared, multiplied by the associated probability. So what I'm going to do here is I'm going to build a table to kind of illustrate this. You work it out. What I'm going to do is I'm going to put the data values across the top. 1, minus 1, and 2. Now, in my first row, I am going to calculate x minus mu. We already calculated the mean. If I didn't have the mean, I would have to calculate the mean because I need it in the formula. So, I calculate the mean. It was 1. 1 minus 1 is 0. Negative 1 minus 1 is a negative 2. 2 minus 1 is 1. Next, notice I have to square it. So in my next row, I'm going to show this being squared. 0 squared is 0. Negative 2 squared is 4. 1 squared is 1. Next, I multiply each of these by the associated probabilities. So 0 times 0.25 is 0. 4 times 0.25 is 1. 1 times 0.5 is 0.5. When I add this up, I get sigma is the square root of 1.5. So I'll leave it at that. You can use your calculator if you want to approximate it numerically using a decimal number. But again, the standard deviation is this formula. So easiest thing to do is build a chart, because if there was too much data here, I'd be using a calculator. I'd actually be using Excel. I don't use calculators, except for small calculations. But anyway, you take the difference between the data value and the mean, you square it, then you multiply that squared difference by the associated probability. So again, for this one it was 0.25, 0.25, and 0.5. Alright, moving on. Number 3. We have something that is normally distributed. Test scores are normally distributed, and the average score is 65. So we know mu is equal to 65. Standard deviation, sigma, is equal to 5. We assume that the scores are normally distributed, and we want to determine the following probabilities. When things are normally distributed, we can convert them using to a z-score. Remember, the typical form to convert to something that is standard normal is given by, I'll put it down here, z is equal to x minus the mean divided by the standard deviation, right? You've been seeing that throughout the remainder of the course. So the first thing, since I want to use the z-table, I need to convert this to a z-score. So 70 minus the mean over the standard deviation. So I am looking up the probability that z is less than 1. Now this is the way the table works, right? The table gives me the probabilities of being less than 1. So if I go to my z-table and I look up z equal to 1, and I have a very slow mouse, so bear with me here. I don't know why, but okay. Here's z equal to 1, and so the associated probability is 0.8413, 8413. For the second one, we have to convert these two numbers to z-scores. So what I'm looking for is the probability that 62 minus 65 over 5 is now a z-score, and then 72 minus 65 over 5, which gives us the probability of being between minus 0.6 and 1.4. Now this is the case where we take the lowest from the highest. So I'm going to look up 1.4 in the table and minus 0.6 in the table. I assume you can do that, so I'm going to just tell you what numbers I came up with. 0.9192 was the probability of z being less than 1.4, minus the probability of being less than negative 0.6. When you look up negative 0.6, you get 0.2743. You take that difference, and that difference is 0.6449. So that's the answer to that one. Remember, between the two values, the probability of being less than the larger number minus less than the smaller number. Number 4, we are under a standard normal distribution table. So I can go right to the table. Most people got this one correct, so I'm going to just kind of illustrate it. You need to be between two numbers. So I need the probability of z being less than 1.2, but I need to subtract from that the probability of z being less than minus 1.3. This is the way the table works. I'll look up these two numbers. First one, 8849. The second one, 0.0968. You can stop the video if I'm going too fast, right? Probably haven't mentioned that till now, but you can always stop the video when you calculate that difference, 7881. The next one, I want to be to the left of z of minus 0.33. Again, standard normal. To the left, that's the way the table works. In other words, this is what the table is telling me. So I'll look up minus 0.33 in the table, and the number I get is 0.3707, and that's the correct answer, because that's the way the table works. Now I want to be to the right of z. So here's z, 1.25. I want to be over here, but the table gives me what's over here, right? That's 100 minus, 1. We're not using percentages in this class, so let me just work it out the way this class is. Minus z being less than 1.25. When you look this up in the table, you get 89.44. When you take the difference here, the answer comes out to be 0.1056. Again, slow down the video. I'm just kind of walking you through quickly those because those are really kind of straightforward. Now, let's look at problem number 5. Suppose it's been determined that for a certain lottery game, the probability of winning is 0.20. An individual purchased 30 tickets, and we want to determine the following probability, that he wins exactly 3 prizes. Well, we're kind of telling you this is binomial, but remember, you have to identify a problem. We're working a problem where there's one of 2 outcomes. You win or you lose. You need to think binomial formula here. Especially we're counting how many successes we have. So in this particular problem, we're looking at the following. N is the number of trials, which is 30. We purchased 30 tickets. P is what we're calling success, and in this problem here, success is winning a ticket, like having a winning ticket. We know that probability is 0.2. Then Q, which is 1 minus that, has to be 0.8. Now, we want the probability he wins exactly 3 prizes. That is the formula. C, we're picking from 30, 3 items. Then you multiply by the probability of success raised to how many successes? 3. Probability of failure. How many failures? Must be 17. Not 17, 27. Because we have a total of 30 trials, and if 3 of them are successful, 27 will have to be failures. When you do the math, I'm going to just round this off to what I have. Okay? Now, I'll just remind you, C of 30, pick 3. You're picking 3 things, so 30, 29, 28. But C stands for you do not care about the order, so you have to divide by 3 times 2 times 1, right? Then you do your math here. That's going to come out to be 0.008. 0.8 to the 27th power is close to 0.002418. When you take and do your math, my answer came out to be 0.0785. Somewhere around there you should be. All right? That's straight up the formula. You identified it as a experiment where you're conducting it several times, and either you have success or you have failure. In this problem here, we want to calculate that he does not win any prize. That is the probability you win 0 prizes. Well, 0 prizes would be C of 30, pick none. 0.2 raised to the 0 exponent. 0. I caught myself with a mistake here. That should be a 0.8. Okay? 0.8. So there you go. Caught myself at least. 8 to the 30th power. Because we don't have any successes, right? Well, C of 30 pick 0. Whenever you're picking nothing, that is always equal to a 1. 0.2 to the 0 is 1. 0.8 to the 30th power is a very small number, but that comes out to be 0.001238, something in that neighborhood, okay? For C, there's 2 ways of actually doing C. You want the probability wins at least 1 prize, right? Now, you could do this by calculating the probability of 1 minus the probability he wins at least one prize, meaning he wins no prizes. But that was done right above here. So actually, you could just take this number here, plug it in here, and you get the answer. But if you choose, because sometimes it's not that easy, because if I would have said at least two prizes, that would not work, because the opposite of at least one is 0. But at least two, the opposite would be 0 or 1. But anyway, I'm going to use the normal approximation just to illustrate that here. So I want the probability that x is at least 1. Okay, at least, right? So to convert to standard normal, I want to include 1. So I'm really looking at the probability of z being greater than or equal to 0.5, because I want to include 1. I want to be on this side of 1. Well, I want to be on this side of 1. I want to include it, so I have to go down to 0.5. Alright? Now, that I've made the adjustment, my next step is, well, I use the fact that we can convert this to a standard normal by calculating the probability that, I'm sorry, this is x. I kind of jumped the gun here. X. Z is greater than or equal to 0.5 minus the mean. What is the mean? Well, for any binomial distribution, sorry, let me put it right here. The mean is n times p, and here was 30. P is 0.2. So n times p is 6. So that's the mean. The standard deviation is the square root of npq, right? So if you calculate that, show yourself this comes out to be 2.19089. That's a 0. When you do the math, the probability of z being greater than or equal to minus 2.51, which is the same thing as 1 minus the probability of z being less than or equal to minus 2.51. When you look that up in the table, you'll see again that you get, well, when you get it, I'm going to just give you the answer here. You should be able to find things in the table. Okay, so 0.994, which should be very close to what you got here. Okay? They're going to be off a bit, because remember, this is the normal approximation. I mean, just mind you, on a final exam, you'll be able to tell that that's the correct answer, right? Remember, we're approximating here, and I told you could do it. All right, moving on to number 6. On average, the mean lifetime of a fluorescent light bulb is 2.1 years. The standard deviation is 0.8. What's the probability that we randomly select a bulb, it will have a lifetime between 1.9 years and 2.2 years? So we're choosing one light bulb, and we're looking for the probability that light bulb's lifetime is between 1.9 and 2.2. We're not calculating the probability of a sample mean. We didn't take a sample here. We're just looking at one light bulb and trying to determine what's the chances its lifetime's between 1.9 and 2.2. Now, assume this is normally distributed, we need to convert to our z-score. And therefore, we're given the mean is 2.1, the population standard deviation is 0.8. So converting to our z-score, 1.9 minus 2.1 divided by 0.8 is less than z is less than 2.2 minus 2.1 divided by 0.8. When you do the math, this comes out to be z being between minus 0.25 and 0.13. So going looking it up in the table, again, this is the where we have to find these two percentages or probabilities. When you do, for 0.13, you should come up with 0.5517. For minus 0.2, you should come out with 0.4013. When you take the difference, you get 0.1504. And there's your answer. So again, this problem was just the probability of a random variable being between two numbers. You're just converting to z-scores. Remember, you have to identify the problem. Number 7's different. If you read number 7, this problem is asking about the probability that the average miles for the sample is at least, well, I don't know what I used on your test, so this might be off, okay? I'm using 25 here, but I forget what I told you use on your test, so this one's kind of up in the air. I had to make a correction to the original test question, if you recall. But anyway, if I remember, I don't know if it's 25 or 25.1. I think I told you 25.1. I don't know. But let's just go with what we have here. All right. When you have a probability about a sample mean, this is the central limit theorem. So we're asking the probability the sample mean turns out to be larger than or at least 25.1 miles per gallon. The central limit theorem tells us X bar has a distribution where the mean is the mean of the population, so in this case 24.5, and the standard deviation is the standard deviation divided by the square root of n, correct? So we know mu sub x bar is 24.5. If you go through your calculation, show yourself that sigma of x bar is equal to 0.35355. Now we convert this to a z-score. Subtract the mean, divide by the standard deviation. When you do the math, you're going to see this is the case where you're subtracting from 1, the probability of z being less than 1.7. And the answer is going to be 0.0446. Okay? There you go. I hope it helps. Every one of these problems is good practice for the final exam. All right? Thank you.